The Himalayas reject outsiders. Before building the highest bridge in the world above a 359-meter abyss, engineers had to tear into the mountain just to deliver the first steel plate. Early survey crews navigated this claustrophobic gorge on mules or rode upstream through punishing currents. Bringing in 30,000 tons of heavy steel, the equivalent weight of 4 Eiffel Towers, demanded brutal geological restructuring. Heavy machinery carved 26 kilometers of transport roads straight into the vertical cliff faces. Workers pack explosives into precise drill holes. The detonation rips the slope apart. Shockwaves rattle the narrow canyon. Pulverized stone cascades into the valley. Engineers deploy pre-splitting blast techniques. This controlled shearing prevents residual vibrations from fracturing the young, unstable Himalayan rock. Instantly, nozzles blast pressurized shotcrete and crews anchor heavy steel mesh across the raw stone face, physically pinning the mountain together. However, the extreme terrain and sharp hairpin turns dictate a harsh reality. How do you assemble a megastructure if you cannot transport whole beams to it? You construct a factory right on the cliff edge. Transport trucks haul flat, standardized modular steel plates up the mountain paths. A precision mechanical fabrication yard operates inches from the lethal drop of the Chenab Gorge. Machinists cut, drill, and fuse raw plates into massive structural boxes on site. Welding giant components inside a cramped mountain yard restricts access to crucial structural joints. The engineering team counters this limitation with extreme mechanical leverage. They build a specialized rotating lever arm system. Hydraulic grips lock onto the massive girder sections. The machine physically flips the colossal steel framework in mid-air, exposing blind spots for flawless, uncompromised welds. A multi-ton beam on a rotating lever arm hovers over the abyss, ready for installation. The cliffside factory was built for a single purpose: to feed steel to this Himalayan leviathan worth $5 billion. The Chenab Railway Bridge shatters every global height record, rising 359 meters above the riverbed. That altitude eclipses the Eiffel Tower. But instead of resting on a paved city square, this iron beast spans a violent geographical void. 359 meters, $5 billion, 20 years, 30,000 tons of forged steel. The scale crushes ordinary logic. Moving these massive components across sheer mountain faces stands as a brutal statement of engineering audacity. Crews suspended colossal segments above the gorge, wrestling with erratic winds to lock heavy elements into a seamless arch. Zero margin for error. Success demanded millimeter assembly precision directly in the air, without a single support from the valley floor. But why spend 20 years on a single bridge? Because this millimeter precise assembly above the Chenab River is the only way to close a 272-kilometer circulatory system of railways. For decades, the Kashmir Valley remained entirely at the mercy of primal Himalayan weather. Every winter, sub-zero winds freeze the landscape, while heavy snow avalanches routinely bury the only existing mountain highway. This brutal cycle physically severs more than 7 million residents from the national network. Complete icy isolation. Breaking the seasonal blockade meant pushing an ultra-modern transport corridor deep into completely hostile territory. High-speed steel tracks clashing against prehistoric rock. Yet, bringing global connectivity to this remote zone required overcoming the absolute worst natural bottleneck on the continent: the Chenab River Gorge. A sheer tectonic fracture dropping hundreds of meters down into a roaring water current. Without crossing this massive vertical void, the tracks would simply dead end at the cliff edge. One structural miscalculation, and this ancient Himalayan trench would permanently bury the entire 272-kilometer railway project. The dream of a 272-kilometer route almost collapsed at the start. When engineers approached the edge of the gorge, it turned out the young Himalayas were literally crumbling under their feet. The crunch of unstable tectonic shale echoed with every step. The rock was broken. These mountains are a highly active seismic zone, constantly pushed upward by colliding tectonic plates at a rate of 5 millimeters a year. The stone along the cliff face was deeply fractured and brittle. Standard excavation would simply trigger a massive landslide. The whole mountain would fall. To prevent a catastrophic collapse, the engineering team had to rebuild the cliff from the inside out. They mapped the microscopic cracks hidden within the stone and deployed heavy drilling rigs. Tungsten carbide bits cut shafts up to 40 meters deep into the fractured mass. Then the high-pressure injection started. Industrial pumps blasted liquid cement grout directly into the boreholes. The colossal pressure forced the thick slurry into fissures thinner than a credit card. It acted as a massive geological glue, The liquid turned into stone. A crumbling, loose slope instantly transformed into a solid load-bearing monolith, ready to handle extreme compression forces. Only on this artificially hardened crust could the core support bases be safely poured. Construction crews worked continuously, rapidly pumping 34,000 cubic meters of concrete into the rock. That is the equivalent weight of a 15-story residential skyscraper physically embedded into the vertical cliff face. Foundations S40 and S50, having absorbed 5,800 tons of steel, firmly gripped the mountain, opening the way to a 359-meter void. The geological foundation is secure, but building scaffolding from the floor of a gorge deeper than the Eiffel Tower is a physical impossibility. No ground-based machine can reach across a gap of nearly 500 meters. To construct the bridge, engineers first had to build a massive transportation infrastructure suspended entirely in the sky. Two temporary steel anchor pylons quickly rose on the opposing foundation blocks. The anchor points were ready. The real challenge was connecting them. Pulling the initial line across a canyon notorious for vicious wind shear demanded an extreme aerial solution. A specialized light utility helicopter takes flight. The deafening roar of its rotor blades echoes against the sheer rock faces as the aircraft violently battles the turbulent thermal updrafts rising from the riverbed. The helicopter slowly inches across the abyss, unspooling a single saving thread from its belly. This is the pilot line. Woven from ultra-high molecular weight synthetic polymer, it is barely thicker than a human thumb. Yet this lightweight rope possesses a tensile strength that outclasses standard steel. The aircraft reaches the far side. The first physical link is established. Now the mechanical scaling begins. A high-capacity hydraulic winch system takes over the operation. The thumb-thick synthetic cord pulls a heavier steel wire rope. That wire pulls a much thicker cable. Sequence by sequence, the diameter multiplies until the massive main superload track cables are hauled up and locked onto the temporary pylons. A monumental 950-meter cable crane network now dominates the sky. The engineering contrast is absolute. An operation that started with an ultra-thin synthetic cord now forms a web capable of supporting 1,000-ton steel bridge modules. The track cables are tensioned to their maximum limit. The overhead trolleys engage, and the first multi-ton steel module leaves the fabrication yard, slowly gliding out into the empty void. Why not just build a standard cable-stayed bridge over this abyss? It would be far simpler to mount pre-tensioned cables from aerial cranes. The answer lies in the invisible but deadly physics of the canyon. Why do flexible suspension structures inevitably face destruction here? The V-shaped terrain of the gorge acts as a massive natural funnel. This is the Venturi effect. The narrow mountain corridor compresses massive volumes of airflow, dropping the atmospheric pressure and violently spiking the wind velocity. Sudden gusts accelerate to 266 kilometers per hour, a Category 5 hurricane. At an elevation of 359 meters, this aerodynamic brutalism completely rewrites the rules of engineering. Suspension bridges rely on tensile flexibility, but flexibility destroys railway transport. High-speed winds generate continuous twisting and rhythmic vibrations across a suspended deck. This is aerodynamic resonance, the exact same physical phenomenon that tore apart the Tacoma Narrows Bridge in the 20th century. A passenger train requires absolute track stiffness, zero oscillations. A suspended deck would simply twist under the aerodynamic assault, dropping tons of steel into the riverbed. To eliminate the vibrations entirely, engineers abandoned cables for a compression-resistant steel arch. The curved geometry dictates survival. Spanning 467 meters, the massive skeleton operates on a single mechanical principle: compressive load transfer. The heavy steel ribs drive the dynamic weight of the trains, and the violent lateral wind strikes outward along the curve. This accumulated energy travels downward and slams directly into the S40 and S50 gravity abutments. The solid mountain rock instantly absorbs the forces. No intermediate piers. Total structural integration. The arch transforms the lethal threat of the canyon wind into monolithic rigidity. But assembling it at a height of 359 meters is a delicate balance on the brink of disaster. To transform this 467-meter steel curve into a weather-beating monolith, engineers had to assemble it piece by piece. The structure grew directly into the void. It was held back from a catastrophic fall by a complex web of temporary cables. Steel modules weighing up to 80 tons slide down from the peaks and lock into the growing ribs. The routine transport is fast. The physics of the cantilever are brutal. As the metal arms reach further out from the abutments, they become giant aerodynamic aerodynamic levers. The canyon wind bites into the exposed geometry. The vibration hums straight through the temporary steel grates, creating a constant low-frequency tremor under the workers' boots. To prevent the heavy ribs from twisting out of alignment, engineers anchor diagonal stay cables deep into the mountain rock. These thick metal ropes act like reins on a massive beast. They sing under immense tension whenever a heavy gust strikes the valley. The real battle lies within the geometry. A steel span nearly half a kilometer long behaves like a living organism. The metal expands and contracts by several centimeters under the intense mountain sun. Surveyors track the advancing ribs with robotic total stations, calculating the precise trajectory against continuous thermal shifts. The contrast is staggering. 10,000 tons of raw suspended weight rely on a geometric tolerance of exactly 3 millimeters. One fractional error at the foundation multiplies into a massive, unbridgeable gap in the center of the sky. Two colossal steel halves slowly converge in the high-altitude air. Surveyors verify the final coordinates as the laser readouts stabilize on their screens. The heavy lifting crane lowers the central closure segment into the narrowing gap. The massive piece of engineered steel hangs just inches above the locking mechanism, hovering completely motionless over the deep gorge. But even a steel arch closed with millimeter precision is just an empty shell. Left as a hollow frame, it will never withstand the powerful seismic shocks of the Himalayan range. The raw metal needs an upgrade. The true engineering secret of the bridge remains completely invisible. Those giant intersecting ribs are actually empty pipes. To survive the extreme geology, engineers pump thousands of tons of heavy, self-compacting concrete directly into the steel veins of the structure. The viscous liquid stone flows upward under intense pressure. Advanced chemical plasticizers allow the heavy mix to move like thick syrup, aggressively hunting down and filling every internal void without requiring a single mechanical vibrator. The empty core disappears. Once the material cures inside the dark tubes, the physics of the entire span fundamentally transform. The outer steel shell absorbs the aggressive stretching and bending forces. The newly formed artificial rock interior handles the crushing compressive loads. Steel brings tensile strength. Concrete brings brute mass. This massive internal injection of weight instantly dampens high-frequency vibrations. The steel frame stops acting like a giant tuning fork over the gorge. The structure locks into a permanently rigid composite monolith, packing enough raw density to stand completely motionless against extreme wind gusts of 266 kilometers per hour. But even the completion of the steel arch did not guarantee triumph. An invisible enemy threatened to tear the bridge apart at the molecular level during a massive 50-degree temperature swing. The gorge drops more than 300 meters down, creating a brutal environmental contrast. Direct sunlight scorches one side of the valley, baking the exposed steel to 50 degrees Celsius. The opposite rock wall traps the remaining sections in an icy shadow. There, ambient temperatures plunge down to 0 degrees Celsius. Heat expands, cold shrinks. Structural steel elongates by roughly 12 micrometers per meter for every single degree of accumulated heat. This immense thermal gradient forces the nearly half-kilometer metal frame into a violent physical tug-of-war. The structure twists asymmetrically. A dull metallic groan and heavy grinding echo across the ravine as thousands of tons of steel literally breathe under the Himalayan sun. The bridge pulsates like a colossal living organism, continually expanding and contracting with the shifting microclimate. Standard railway engineering demands rigid connections. Here, rigidity equals disaster. If construction crews welded the tracks directly to the shifting deck, unyielding thermal stress would violently buckle solid steel. Total derailment follows. To isolate the trains from the moving frame beneath them, engineers entirely abandoned traditional fixed welding. Instead, they mounted the rail line on an advanced network of guided sliding supports and applied precise structural pre-stressing. This intelligent sliding mechanism smoothly absorbs the deadly metal tension, preserving the exact geometry of the track. The arch was finally rigid, locked in place by a heavy concrete core system. But to even lay these sliding rails onto the bridge, engineers had to solve a macro problem, launching a single continuous deck over the abyss. Cable cranes quickly planted vertical steel columns along the upper curve. Now came the deck. Normally, builders drop bridge sections from above, but valley winds whipping at over 100 kilometers per hour turn suspended steel into uncontrollable sails. Cranes become death traps. One gust dust means disaster. Instead, the team deployed the incremental launching method. Welders assembled the entire deck on one solid edge of the gorge. 10,000 tons of steel fused into one continuous structure. Massive hydraulic jacks engaged. They pushed the colossal mass horizontally out into thin air, driving the heavy metal forward like a giant blade sliding into an invisible sheath. Step by step, the hydraulic system thrust the steel over the support caps until the massive deck crossed the void and rested firmly on the opposite cliff. When the final span rested on the pillars, a 20-year war with gravity, wind, and temperature reached its historic conclusion in the summer of 2024. The first test train rolled smoothly across the Chenab River. Beneath the steel wheels gaped a void of 359 meters. This altitude eclipses the Eiffel Tower by 35 meters, a towering record carved into the sky. For the first time in history, the heavy blast of a locomotive horn echoed through the deep, isolated gorge. The sound bounced off ancient rock walls, announcing a permanent geographical shift. The colossal arch now hangs in the harsh Himalayan winds as a solid ribbon of steel, permanently stitching together the fractured landscape of the mountain range. This structure represents far more than a mechanical milestone. It serves as the master key to the Kashmir rail corridor. For centuries, brutal winters and treacherous passes severed entire valleys from continental trade routes. The bridge erases that isolation. An unbroken economic lifeline now pierces straight through the geological barrier. Engineering intelligence defeated the absolute blockade. Masterpieces of modern mechanics constantly rewrite the limits of global infrastructure, inviting endless exploration into the ambitious megaprojects that reshape our world. The blast of the locomotive horn gradually dissipates down the valley. The rhythmic clatter of the heavy steel fades away, leaving behind only the quiet silhouette of the highest railway bridge on the planet, permanently frozen above the drifting clouds.